The Sporlan division of Parker Hannifin proudly sponsors the Advanced Refrigeration Podcast. Contaminants like water, acids, sludges, and varnishes may react with compressor windings, leading to compressor burnout or cause copper plating, which reduces bearing clearances, or poor valve seating, eventually causing failure. Or they can deposit in the expansion device, restricting flow or proper modulation of thermostatic expansion valves. Loss of superheat control will lead to lack of cooling if the evaporator is starved, or even worse, flooding of liquid back to the compressor, causing bearing washout and eventual compressor failure. Installing a properly sized, high-quality, time-proven Sporlan catch-all will ensure contaminants are captured before they can harm the new system components. Ask your local refrigeration wholesaler about the Sporlan catch-all filters. Parker Sporlan, leading the charge.
We started last week, so hopefully I don't screw this up this morning or this afternoon. See, I'm already messing it up.
Screw what up?
Just talking in general.
You're good at that. That's all you do.
Maybe I should start reading some comics, like some manga. Wouldn't that be cool? Start reading some of that manga comic.
So dumb.
I know, it's retarded.
Embarrassing.
You just can't let anyone know that he reads them. Good afternoon, everybody. Welcome to Advanced Refrigeration Podcast. You're the host, Brett Wetzel and Kevin Compass. What are you doing? What do you say?
Today I played oil bath roulette this morning.
You made the kid do it.
I did the first one, and yeah, I don't know if anybody's ever had to change on the old Hill screw racks with the Carlisle 06Ts, the oil filters that are on there. They're like canistered hydraulic oil filters from Carlisle. They are awful. Like, it's a trap. Like, you're either it's like Schrodinger's cat. You're getting a bath or not getting a bath. There's no in between. Like, the drains on the bottom of them get plugged up with stuff. You got to wiggle it back and forth, go real slow. But if somebody's a dickhead and double O-rings it, and it'll wiggle a little bit out and then it'll seal again. And then next thing you go to pull it, and out comes a half gallon of oil at Mock Cheese's.
Well, only a half gallon? Only a half gallon?
It depends. It literally covered me head to toe the last time. I was being real cautious about it. I'm sorry.
What happened?
I just looked at a text message from Dylan.
What did he say?
I'm not telling you right now. Yeah. It's a toss up. So like I usually get a cardboard shield and try to like protect myself from it because you're getting a bath. And then we were doing the suction filters and it was just fucking oil everywhere.
I saw like the kid was behind that piece of cardboard, like he was like fighting off The Walking Dead. Like he was like braced up behind it, like waiting to get him.
Well, the last time I did one, I was going back and forth and I wiggled it and it didn't, like, nothing came out. I was like, okay, cool, it's dead. I went like another like half turn and it fucking shot off like a missile. It hit the ground at like full pressure, 160 pounds of discharge pressure, hit the ground, bounced up, hit the ceiling of the rack house, and bounced down again. Like full pressure, like just send it. And yeah, I don't know. It was not good. So I'm very cautious when I do those from now on because of those situations. But like even the liquid cores are full of oil. Like this rack is all messed up. And
wait. How are the liquid cores full of oil?
I don't know. Like I didn't get that far.
How is that
like
a thing?
we changed cases over here and we were just doing the post construction and this is somebody else's. They have in-house techs, so this is on them. But yeah, there's definitely some oil issues there, obviously. This thing's like a modified loop, not loop. Also was glycol at one time and Pecasol, and it's been converted.
What's Pecasol?
Pecasol is the worst idea ever to grace anybody's engineering desk. It's a low temp brine fluid.
Oh, that's that stuff that you said like eats through like everything?
It eats through everything. It eats through fucking solder and pipes. It eats through rubber. It eats through, you name it, like wiring. Basically shrivels up everything. It's awful. Like all the stores still stink like it. Like all the compressor rooms just smell terrible from it. Like it's soaked into the concrete.
It's awful. Oh goodness. What have I been? Absolutely just I'm making curriculum. Like I said, I trained last week and I ended up potentially getting some other stuff that I think that I'll be able to do within the next, probably after January, but just trying to make as much curriculum as possible. I'm working on ViRegard training right now, which I was doing all right on time. And then all of a sudden I then realized that I had goofed up royally and didn't make the pipes big enough for what I was doing. So when I went to go fill in the color, it didn't go as well as what it was supposed to. That's the thing. So I had to go back and redo literally everything that I was doing as far as like I had to make the rack over again. And then I had to figure out a creative way to make it colored behind every single one. So I differentiate what's the suction, what the liquid was, yada, yada, yada. Yeah. So I guess we're going to talk about some basic refrigeration stuff, right?
Yeah, let's do some basics. I had some guys asking for some like basic 101 and stuff like that. So let's go over some basic stuff.
All right. Bring some stuff up. That. Isn't that cool? Awful.
He's gonna kill you. Oh, I know. It's gonna be hysterical. Anyway,
So I figured that we'd start off basic just by talking about superheat, and we could probably get a conversation going about that. And then after that, we'll start into some other
God, you're
basic
so
stuff.
awful.
Just today.
You're so awful. It's so funny.
One that's rude. Anyway, so superheat. We're trying to make sure by checking superheat, we're checking to make sure that we're utilizing every bit of that coil. The less superheat we have, obviously, means that the coil is going to be filled all the way to the brim. Typically, you have evaporation going off where you're not having a temperature change up until the last line within the coil. So a lot of times, like we're doing some diagnostic on a coil and we have some issues that are going on. A lot of times what I'll do is, and I know you've done this too, especially with a unit that has like a distributor on there, putting a temperature sensor on the U-bends. Seeing, so if you're saturated, like in this instance, I have a saturated of 20 degrees. So that means we should get 20 degrees, 20 degrees, 20 degrees, 20 degrees, 20 degrees, all the way up until the very, very last pass. And that's essentially when we should be start to superheat. And talked about this before. Well, I'm a firm believer on 3 to 5 degrees of superheat for our low temp stuff and 6 to 8 for our medium temp. The only off ones that I do about that one is doing the 3 to 5 degrees for some of the coffins and 3 to 5 for some of the low profile stuff.
I run 3 to 5 for everything.
Do you really?
Yep. Lower the better. 3 to 5 for everything.
Yeah. No. But what happens?
I've been doing it for years. Zero issues.
I follow whatever the spec was of the manufacturer.
What about with all the old cases where it was 10? Got you there.
I don't want to talk about the old cases.
I
So,
don't want to talk about the old case.
typically, I'll let you, you know what, talk about Glide, and then we'll bring up the whole TD thing.
Okay, glide is the difference between your dew and bubble point. So you're going to have two different refrigerant temperatures for a given pressure. So on the PT chart, if you look at, you got dew point, you got bubble point. Okay, dew point is going to be for your evaporators, suction control, EPRs, anything like that. Dew is for superheat. Bubble is going to be for subcooling, condenser control, stuff like that. Midpoint. Go ahead.
Sorry, I had someone yell at me the other day because they're like, "No, that's wrong." I was like, "No, I don't understand why people think it's the other way around."
No, it's definitely not. So midpoint is essentially a made up number. It is a guesstimate of the average of the glide in a coil, in a rack, in a condenser. So a lot of people run off midpoint. I'm starting to not run off midpoint on stuff. I'll raise the suction set point up, or I'll do it like that because it always throws off the superheat calculation in the suction groups. So when you run midpoint, because it's not how you calculate superheat. You don't calculate superheat from midpoint. Calculate superheat from dew point only. Subcooling, same thing. You calculate subcooling only from bubble.
So, wrong one.
Midpoint is a made up number, which you got right here. So if you look on here, you got a liquid, 449 liquid and a 449 vapor. So if you go to 20 pounds, for example, or sorry, 20 degrees, sorry, go to 20 degrees. It's okay. So you have 57 pounds or 44 pounds. So it's a pretty big difference. So you calculate your glide by subtracting the difference of the two. So 57 minus 44. And that's going to give you
What your glide is.
Yeah. To give you what your glide is. Now, it moves as you move on the PT chart. It's never a set number. Usually it moves on the PT chart. It's not like dramatic. But it still moves.
You mean it's not directly linear, right? You're not going to have the
Correct.
even amount of glide throughout. It's an average of, like, on the lower end, it's about what, 10 degrees, 9 degrees, somewhere in that wheelhouse.
Correct. So it's moving.
Gotcha. So if you're setting up, when we talked about this a while ago, so when I do pressure controls, I try to do with what the midpoint is, because you have that, you're getting a little bit cooler, a little bit warmer. I'm going to find another PT chart. Keep talking.
So
I'm going to find a PT chart.
I don't like doing that, just for the simple fact that as I've been programming more and more stuff, it throws off the superheat calculation in the suction groups. Because if you do it off midpoint, then the superheat calculation's shit. It's usually 4 or 5 degrees off. So then it confuses people. I usually just end up raising the suction set point up enough to account for the glide. But that's all you're doing. Raising it up is doing the same thing. But programming as midpoint is a made up number.
Yeah,
it all works the same.
I got you. This took forever. Why? I got you freaking internet, and you're just being a piece of shit. All right, hold on. So I like this way better, like when it shows the pressure, and then freaking bar. Really? Out of all the feature.
Yeah, like, why is it even 449 in bar? Like, really? Is everything like 30 bar and down? Yeah, it's 34 bar and down. It's hilarious.
Never mind.
2 starts.
Continue with what you're doing.
Yeah, so that is what midpoint is. Now, if you look at an evaporator, when it's going through, you're never going to be at a true dew or bubble point. So that's where midpoint comes in. As you're boiling off through the evaporator, you're boiling off refrigerant at different rates because all these gases are mixes of different refrigerants. So certain refrigerants are going to boil first. Certain refrigerants are going to boil last. Now, as it's going through there, obviously it's changing its temperature pressure relationship. So you got to really watch it. So that's where midpoint comes in. Now, when you're setting superheats, dew point is the only thing I care about. I want to look at my dew point, and that's what I'm setting my superheat off. If I'm checking subcooling on a condenser outlet, I only care about bubble point. I'm not looking at midpoint. I'm only caring about bubble. Mm-hmm. Same thing if I'm doing a non-condensable test. I usually give it like 2 or 3 degrees of leeway with that and around that number, because you're never going to be exact because it's a makeup of different refrigerants.
Gotcha.
And fractionization is like the biggest made up thing ever.
So I'm gonna disagree with you, only because so on 448, 449, it's not as much of a thing, but some of these other gases, replace. It was like the R22 replacement. It was some HVAC one, 422B or some bullshit.
Well, that stuff is like just poppycock,
awful.
Terrible gas. Like
it's awful.
Yeah, like that should have never even existed.
So so the reason why I'm saying that is, so this guy had a distributor, and the unit had been installed with R22 forever. And what we found out is that the distributor actually, like, one of the lines was longer than the other. And just because of that mix of when that refrigerant's boiling off or whatever, because of that, he ended up having uneven distribution, like as far as the coil frost pattern. He's like, it's been like that way for years. I'm like, R22 was a great gas.
It did. It was. Not that though. Like that gas was awful. All the 422s were awful. Those were high glide refrigerants. They had like 10, 12 degrees. Some of them even had 14 degrees of glide. Now, glide isn't always a bad thing. Glide helps us at times because we get a little bit more efficiency out of glide, because that evaporator can be ran a little bit higher on pressure. The compressor, all it cares about is pressure differences and the temps coming back and how efficient it becomes. The higher you get the compression, the lower you get the compression ratio, the more efficient that compressor starts to get. So that's where these glides come in. You may be able to go up from an R22 conversion on 448 or 449. You may be able to go up a couple pounds on the set points, which is going to buy you a little bit more efficiency.
Oh, because you have that glide, your coil's running a little bit cooler at times, right?
Yeah. Your coil's be able to run a little bit cooler at times. Now, when I'm setting EPRs, I will use midpoint generally. I will get them close with midpoint and then just go from there. Because if you set a meat case at a plus 28, like plus 25 degree evaporator temp on dew point, you're going to be readjusting it later. It's going to get too cold.
So you're doing the split. Are you doing the split between here?
Yes.
Okay.
I'm doing the split between there.
Yeah.
I usually use this Sporlan Smart Tools app because it actually lists the glide next to it.
Mm-hmm.
You get for that pressure, it'll actually list the dew, bubble, and then glide. So that's one thing to keep in account. And then some EMS controls, like Danfoss, for example, they either list it dew or bubble. They don't list it midpoint. But microthermal, you could choose CP or Copeland controls an E2 or E3. You could choose. So it just matters which one you choose and choosing it right. And you just remember, like, that bubble point is for condensers and receivers, and dew point is for evaporators and suction control.
Okay, so if you're doing, all right, so if we're doing 20 degrees, right? So this is all the pressure. 20 degrees right there would be sorry, wrong way. 20 degrees. So we have 20 here. So are you doing a mid of 40, let's see, 48 or something like that?
Yeah, right around there. That's about right. Give or take a few pounds as you have to adjust it.
Yeah, and you'll notice your coldest SSD case on the line won't be able to pull down the temperature because you don't have that cranked all the way down. Right? The game is not having to run. Sorry, not having to run the thing all the way down as low as humanly possible.
Yeah, no, that's a huge thing. So that's why glide isn't always a bad thing. And everybody says setting superheat with 448 and 449 is terrible. I don't think it is. Like when you have a valve that's hunting and you seem to get some hunting on 448 and 449. The best thing I find is to open it more.
Say that one more time. Sorry.
When you get a valve that's hunting, especially on 448 and 449, where it's just like all over the place, and everybody says it's more difficult to set superheat on those two gases. Like I generally will open the valve more. And
so it doesn't hunt as much.
Correct. It usually stops the hunting is running a lower superheat.
One of the things that I found is sometimes with running because I know Kevin is, but I am as well, is like setting the SSD whatever it's supposed to be like on the subcoolers and that. And sometimes that can be difficult because we want it to operate at the temperature that we want it to, but we don't want it to keep cutting in and out. And so sometimes you have to run a little bit higher than what it says on the actual reefer schedule, right?
Well, I mean, most of the time it's like 10 to 15 pounds higher than what it calls for.
Yeah, because otherwise, then for some odd reason, like probably because the pressure's changing, unless there's an EPR in there, it ends up flooding back hard.
Yeah, no, well, the other thing is all these manufacturers underrate those heat exchangers. Like they are efficient. Some of them have like 2 to 3 degree approach temp on them.
Yeah.
It's way more efficient than what they say it is, which is a good thing. There's nothing wrong with running it more efficiently. You're running a higher saturated temp. So this just subcoolers, that's a big thing, setting it up.
So not only for utilizing superheat for evaporator efficiency to make sure that we have the right superheat, but also utilizing it to make sure that we're not flooding back. All HFC compressors typically have a minimum superheat of about 20 degrees. We don't want to go any lower than that because then we potentially run the risk of getting a little bit of liquid in that oil, getting some kind of oil failure, but also checking superheat on the discharge side. A lot of times if you're trying to diagnose any kind of compressor issues, if you have a common suction coming back, it's all the same pressure, all at the same temperature, but you have one compressor potentially running higher than some of the others, chances are we have some kind of issue. We do not have the correct amount of lubrication because of a blocked pickup screen. Maybe we don't have enough oil in there. Give me some other things, Kev.
Bearing wear, blow by, oil pot that's stuck on a high pressure oil system where it's just constantly injecting oil into the side of the compressor.
Yeah, and then if the thing empties out and you're just sending freaking discharge gas.
Yep.
Right.
Another thing is there's also discharge superheat.
No, that's what I was talking about.
Oh.
So we talked about suction superheat. That's why I said check the discharge temperature and then checking the discharge superheat. And it's done the exact same way. And then you would use, because you are doing superheat, use the dew point side of the PT chart.
Yeah, so I just had a fucking mental.
No, you're fine. I didn't know if you were getting another text from your brother. He's texting.
No, my brain's just stopped working. Yeah, discharge superheat's a underused thing. Like CO2, it ends up getting used a decent amount. Is watching your discharge superheats, and a lot of flooded evaporator stuff, like especially chillers, they rate their performance on the discharge superheat, what it's doing, not suction superheat, because it's so low on the suction superheat, you may not even be able to measure it.
Yeah, they do that as well for whatchamacallit. Oh my God.
I just want to say that like the discharge line's not in the right spot on this.
I did know, as you were talking, I did notice that.
Today's episode is sponsored by the RefRushield RDP Series differential pressure monitors from Westermeyer Industries, now available for transcritical CO2 systems in addition to other common pressures and refrigerants. When the filter element of your coalescing oil separator is contaminated, it can hurt your system's performance and efficiency. But how do you know when it's time to replace that filter? Wait too long to replace, and you could end up with a nasty filter blowout. But replacing too often can be a waste of time and money. The answer is installing a differential pressure monitor. The RDP Series differential pressure monitors, including the new transcritical CO2 model, are available now from Westermeyer Industries. To find out more information, email sales@westermeyerin.com. That's WESTERMEYERIN.com.
I knew it was going to drive you insane.
This is, you got to remember, this is like my
I know.
dumpster fire of just shit. So, jerk. Out of all the nice things I do, and you just break my balls, it's fine. But, and they're also, the one affects the other, right? So if you have a high superheat coming in on the suction side, you will see, and it's pretty linear. You come up with a couple degrees on the suction superheat, and you'll see it in the discharge line as well. So any kind of bleed by from, let's just say, the hot gas rack, you have discharge gas. So let's say there's 5 compressors on the rack. This one's all the way to the left. The other ones are all the way down on the right, and you're getting discharge gas blowing by because of a suction stop or an EPR shutting. You will see that superheat start to rise up because you are, in fact, dumping that discharge gas directly in the ass into the suction, which inherently is raising your suction, but it's also raising your discharge line temperature. To find that out, you have to put in all the parameters in the Copeland mobile app or the Bitzer app, hem at it, find out what the discharge superheat's supposed to be.
Yeah, the discharge temp even supposed to be like, that's a huge troubleshooting tool too, is the discharge temp. But like discharge temp is a huge influence from suction temp and discharge pressure. So, and compressor efficiency. As the compressor wears more, the discharge temp's going to go up more. So that's another thing to keep in account. Now, checking basic things like going through and checking oil pressure. So basic oil pressure. So you're going to be, do you got anything like that or no?
Not for exact. I got something I'm going to bring up here in a minute.
So checking oil pressure. When you check oil pressure, you're going to go 1 gauge on the pump, the oil pump outlet, which you can see on the compressor right there is the very front. And then you're going to have 1 gauge on the suction service valve. You want to be on the crankcase technically, but a lot of compressors don't have a tap on the crankcase. So if you get to the point where you have a pressure difference between the crankcase and the suction bell end, then that's something when you're going to have to add it. I've had 1 check valve fail on me in 13 years. So
that little 3 PSI check valve or whatever.
Yes. Yep.
Awesome.
That's not a huge thing. So what you're going to do for net oil pressure is you're going to subtract the pump outlet pressure minus the crankcase pressure. And that's going to give you your oil pressure, your net oil pressure. So on a Copeland, generally you want to see 40 to 50 pounds is a healthy compressor. Get below 40, anything below 40, your screen's probably plugging up or you have bearing wear. There's something wrong. Bitzer, same thing, about 40, 45 pounds is a good running Bitzer. And that'll give you a good run. Carlisle's it depends on the year. Some of them are like 15 pounds. Some of them are like 25 or 30 pounds.
Yeah. So if you're going to check it via right on the front here, right where that little brass fittings there. And then Kevin's right. You should technically check it from your crankcase, but in how many years? I don't think I've seen maybe 20 compressors that actually had a tap on the side there.
Yeah. And I'm not installing a tap just to check oil pressure real quick, if I'm getting that deep into it, let me ripping the compressor apart anyway.
For sure. The other thing is too, it also depends on the system that you have, right? There could be other things affecting low oil pressure rather than just low oil pressure or not enough oil. You could potentially have, like in this instance, I have all these compressors basically externally equalized on the oil pot. So you can have
Yeah. Gross.
Yeah. It works when it works. But when it doesn't work very well. If you have blow-by on this compressor, what could potentially happen is you could have this compressor, this one that's blowing by, but that fails all the rest of these compressors. Pressurize crankcase, which will pressurize the oil pot, which will pressurize this line up here, and shove all that pressure in all the other crankcases, essentially rising the crankcase pressure here. A lot of times what I'll do is when looking at these, sometimes you'll see some turp. If you look at a sight glass, it should be the straight oil in the bottom, and then you'll see vapor, but it's not going to be like misty. It's not going to look like smoke. If you look up above of a compressor that's potentially having blow by, you'll see it looks almost like smoky on the top. And I mean, the way I do things, if I suspect that one of the compressors is blowing by, because that smoke will transfer to all the rest of the crankcases, a lot of times I'll shut down one and see if it stops the smokiness in the other ones. If it stops the smokiness in the other ones, then I know that's the one that's blowing by.
I love how that picture has ball valves on both sides of the oil separator. That's the biggest myth out there.
What do you say to me all the time? You're living in theory land.
Yeah, you're
I'm
living
just showing what it
land.
should look like.
You're living in magic land. That's an untouched rack that some service guy hasn't got pissed off and just burned another ball valve in. You're lucky if there's one ball valve. But no, that's a good explanation on blow by. The feeding into the oil pots. Generally, when I'm checking oil pots, I'll just grab with my hand the inlet line. And if you got one that's feeding all the time, generally it's not good. So if you're feeding all the time on an oil pot, generally there's an issue there. You may be moving more oil than you're using, or you have some other issue. But if you feel it, this is a low pressure oil system. So you drain out of the separator through the filter and then drain into the reservoir that's been into the suction. If it's moving that much oil and it's still hot, almost discharge temp hot, you probably have a compressor pumping oil.
Yes, sir.
If it hasn't cooled down a little bit. And if you're running full discharge temp oil, there's a compressor moving a large amount of oil. It's separating it and bringing it right back. The separator's doing what it should, but it's also hiding a problem.
For sure.
What would you say an oil pumper is? Usually like 5 minutes?
Even 10 minutes. Most compressors will hold, like, you could valve off that oil valve and that one. That compressor would stay filled with oil. If no blow by, 35, 45 minutes, even an hour, I've seen. It depends really how low your compressor
35 minutes is pushing it, I feel like.
I've seen it. It depends on how hot it is too, because the higher the compression ratio, the more heat, the more oil it's going to use. So fall day, when it's like winter in Texas, you could actually see it like go 35, 45 minutes without it, emptying it out. And like I told you the one night, man, I had one that was literally, I shut off the main valve here to change out the oil filter. Literally when I do that and I went to go do something else, 2 compressors like instantly filled. It was like a minute and a half. It just railed out that fucking oil. That was that one where every single compressor was shot in the rack.
Yeah, see, that's wild. Oil problems like that are a pain, but that's why checking discharge temps and oil line temps are key for that, like knowing what that temp is. If you got a compressor that's continuously feeding and you shut it off and your oil levels come back, that's a huge, find there. You may have one compressor taking them all down. That's why I don't like equalization lines. Brett has his feelings about them, but I think they cause more problems than they solve because you lose one compressor and it takes up the whole rack.
And I agree with you. The only problem is if you don't have like certain things set up within the program, a lot of times, like I've seen systems where, let's just say this compressor, I don't have a suction drawn up on here, but if this is the compressor that's pulling back the suction, and it happens to be one of those older green compressors that are not Copeland's, if it fills up with oil, like anywhere past the level that it should, a lot of times it will grenade. And so that's the point of the oil equalization line. And I don't want to beat the horse with the oil troubleshooting because I want to do a whole episode like this, but explain that. But real quick, if that compressor fills up with an abundant amount of oil, because that's the compressor that's primarily running, and it does fill up with an overabundance, it will actually push out that oil and put it into the other compressors to maintain the same load. I will also tell you the compressors have to be the same size as far as how high the crankcases are. So if you have a 60 here and a 3D here and a 3D here, you can't really share the 3Ds with the 60 because of essentially the height of the compressor on those big green ones. Because otherwise it's gonna act like a low point and go to the other one. Yeah. But yeah, let's skip the rest of the oil stuff because like I said, I want to do high pressure, low pressure oil system all on HFCs. I want to draw up some more of these so we can go through with a fine tooth comb, talk about venting to the suction, and so on and so forth.
I like it.
So we'll skip over to doing subcooling.
So subcooling, guys, is going to be your bubble pressure in saturation and your line temperature, your drop leg temp, your receiver outlet temp, your receiver inlet temp, liquid line case. These are all expansion valve, liquid inlets. These are all spaces you would choose subcooling. Subcooler, that's a little bit different, but this is essentially what you're doing. So you're converting your saturated temperature or your pressure to saturated temperature, and you're using bubble point, and then you're going to subtract your liquid temperature out. That's going to give you your subcooling. So generally on a grocery store condenser, we may see maybe 3 to 5.
Yeah. No. And then unless, okay. So
Wintertime.
Okay. So anything above 75 degrees, we should get that 3 to 5 degrees of subcooling. Anything lower than that on the ambient, because now the condenser is uber big, and now it's going to be able, that subcooling is going to go exponentially, just ridiculously high. I remember actually when I first started talking to Squires, we remember he sent us that picture where it was like the drop leg line was literally iced up. It was at like 30, 32 degrees, or it was it was like 20 some degrees. That whole line was iced up, even in the mechanical room.
That's EnviroGuard, and that's a completely different animal, and that is my favorite rack ever. And the zero zone ones are my top racks. I love those things.
So on this one, I did 168 pounds. So the saturated for that is 90 degrees. So in essence, we have 85 degree liquid line temperature. So there's where our 5 degrees of subcooling is.
Now, why don't you talk about approach temp? Like condenser approach temp.
Like that?
It would be leaving liquid.
I see. I think, okay. So you talk about that because I talk TD. Basically, let me do the TD and then you can talk about the approach. TD. So if you look at any refrigeration schedule, typically the TD will actually be on the condenser function of the refrigeration schedule. It'll tell you the fins per inch, blah, blah, blah. It'll tell you everything about the condenser, the voltage, Well, in the summertime in Texas, happens to be right. But anyway, rule of thumb, usually 12 to 18 degrees for medium temp systems, 8 to 12 for low temp systems. And if you're doing like a single condensing unit, an RCU or whatever, those have about 20 degrees of TD. So what does that mean? That means if the ambient temperature is 90 degrees outside, if it has a 20 degree theoretically TD, then that means we should get about 110 degrees saturated condensing temperature. And usually that's what, if I'm doing a PM and it's warmer out, as long as it's above 75 degrees, you can look at that and say, oh, okay, it is running the TD that it's specified for. And if it's not, then it's a good indication. Get your ass up there and check out the fans. Make sure the fans are going the correct direction. Make sure the fan blade on the shaft far enough that it should be. Maybe the condenser is blocked. We got some head pressure type controls like we were talking about before, about 2 weeks ago. We were talking about
maybe the whole bottom of the condenser's gone because they had a sprinkler on for 2 years.
Yeah, that could be a good possibility. We were talking about how the receiver repressurization valve is feeding from meow to meow, like into here. That's where we talked about where it could rise your pressure up, which would essentially raise your TD when it should be. Thing that happens with those CROT valves all the time. So that's essentially TD control on there. And we used to do pressure control for everything. Now it just seems like everything is TD control because it's more energy efficient, right? They're not trying to get those fans to keep cycling on and off. We're not hitting utmost low pressure. We're essentially just running the fans to control that TD constantly throughout the operation of the condenser.
We want to maintain the condenser in its design state, so that way we aren't using too much fan horsepower to bring the pressure down, and we don't want to sacrifice compressor horsepower for fan horsepower. At some point, it becomes more expensive to run the condenser than it does to run the rack. So you hit a point where you stop saving energy when you get down too low of a head pressure and you start using more energy than you're saving. So that's why we're using TD control. Now, approach temp is going to be your leaving liquid temperature, so your droplet temp, and then your ambient air temp. So your approach is going to be your leaving droplet temp of a condenser or evaporator, and it's going to be your leaving your air temp or your fluid temp. So like for a chiller example, an approach would be your saturated suction temperature minus your leaving fluid temp.
Yes.
So
yes,
you want to have a tight approach like an evaporator. On a condenser, you want the smaller the approach, the more efficient the coil is. The larger the approach, the less efficient the coil is.
So my question is, because I don't think I've ever seen that on a reefer schedule.
They don't ever put it on a reefer schedule, but if you're troubleshooting like glycol racks and chillers, like approach is a big thing. Like that'll tell you if there's something going on with the evaporator, if it's fouled up. If you have a super high approach temp, like you have a fouled up evaporator or condenser, like we have a lot of water cooled racks up here. You will see approach temp on there. Like we have a lot of water cooled racks inside the bottoms of basements, and you'll see, okay, maybe have like a 5 degree approach temp. That's your version of TD because we're using water. So that's how you would measure the TD.
Okay, I'm sorry because I was confused because you were talking when you were talking about approach temperature. I thought you were talking about doing approach temperature on the regular standard refrigerant, but you're not. You can't.
Yeah.
See, I've never like whenever I've heard of approach, it's always been liquid temperature, right? So you're leaving your liquid coming in versus, like I said, your saturated condensing temperature, and then the same thing with the chillers.
Yeah, you can do the same thing with air. So air temp and leaving liquid temp. So if it's 90 degrees outside and you're 95 leaving, liquid temp, you have a 5-degree approach temp.
What I mean, I'm gonna ask because I don't fucking know. What are you looking for as far as approach temperature on an air cooled condenser then?
Generally, it's within 5 to 10 degrees of ambient. If it starts getting up much more than that, it's when you usually start seeing them fouled out, meaning like dirty, your fan's not running. A super high approach temp is a fouled, inefficient coil. A low approach temp is a efficient coil.
All right. How about, since we're talking about condensers right now, how about on an open loop tower?
So an open loop tower at the rack, I would 3 to 5 degrees if it's a braze plate heat exchanger. Generally, it's 3 to 5 degrees. If
Okay,
it's a
so-
shell and tube, it's going to be more.
All right. So let's just say, okay, so we have an open loop cooling tower, and if no one knows that means that the water runs outside over the tubes of whatever. It's just dropping the water to evaporate, dropping back down in the basin, goes to a braze or a plate and plate heat exchanger, and then goes back up. So it's open to the atmosphere, which sucks because a lot of times, yeah, it's a dirty tower because you end up getting all that shit, all that stuff back into that plate and plate heat exchanger and causes it to be fouled up. So you're saying that it's 3 to 5 degrees within an ambient?
No, it's 3 to 5 degrees within water temp. So if your water temp's 90 degrees, you should be getting like 93 to 95 degree droplet if you're leaving liquid.
Gotcha.
If it starts creeping out more than that, some of the stuff's 2 degrees. Like I was looking at a chiller the other day, like a package chiller unit. It was 2.1 degrees was the approach temp.
Okay, and then you said for a
shell and tube generally is going to be more. So like maybe 7 to 10. It's usually listed on the legend, but it's going to be more. As the approach temp starts getting higher, like you could graph it over time and you could watch it as it starts creeping up. Okay, it's falling out. I got calcium. I got dirt buildup in there. I need to punch the tubes, or I need to run descaler through it and then ruin it somehow. I refuse to descale heat exchangers. Like, we pay an outside company to do it now.
They do it enough that they know. So I worked at a chocolate plant when I was back in Pennsylvania, and I don't know how this is even possible, but they had an open loop that all the water cooled condensers went to, and they also had a loop for one of the byproducts of making chocolate is cocoa butter. And I don't know why this is even a thing. I don't know what engineer was like, you know what? We need a bypass that goes from the open loop to the cocoa butter loop. And apparently someone opened, I swear, I'm not even joking. So what happened was someone opened up that ball valve and ended up putting cocoa butter into all the water cooled condensers.
Sure, that went great.
For weeks and weeks, I'm literally punching tubes. And at the end of the tube punching, at the end, you had like a small stick of butter that would just pop out of every single line. And not every single one had punchable tubes. So I had to, and I don't like using it. I had to use that really gnarly acid that you buy almost like a fish pump. And it's a submersible, like a small little sump pump. And it just takes that chemical and just runs that shit through. I have one that I did on a YCWA chiller, and that return, the shit was green. It was like a dirt mud brown after it was done through. Wasn't fun.
Yeah, no, we just hire a chemical company now because like you could easily screw up the fucking concentration and really mess some stuff up. So that's why we're dealing with that. Like I generally just hire it out. Plus, most of these stores are in big buildings and they prefer you to use their chemical guy.
I have an idea. So what I'll do is, since I'm making a whole bunch of stuff, I would love to explain. Unfortunately, I don't have anything like made up for right now, but I'd love to explain on how to back blow an open loop tower. We had one here in Dallas years ago. Guys were all fighting with it. They couldn't figure out why the unit was going off, and there was like 5 or 6 of the guys there, and they called me up, and I was like, hey, it sounds like the approach wasn't shit for the open loop, and it ended up. Greggy was actually out there, and they took a vote whether to listen to me or not, and they ended up back blowing. It worked fantastically, but I don't think there's up by you. There's tons of open towers, but here in Dallas we don't have, not for any supermarkets anyway.
Yeah, we got a lot of them, but like a lot of them have been switching to open closed loops. So they have a heat exchanger up in the mechanical room that they're running glycol through, and it's got another set of heat exchangers that the tower loop goes through.
So the water, all it's doing is just going over the tubes that contain the glycol, goes to a brazed plate heat exchanger, and then there's another glycol that's transferring that heat from the other one.
So what you generally have is you get the open loop tower, and it's going to a giant braze, not a braze plate. It's a
Shell and tube?
Plate and frame.
Plate and frame.
So giant plate and frame heat exchanger, which a plate and frame heat exchanger is the same thing as a braze plate, except you can remove the sections and clean them and put them together and replace them.
Yeah, I'm sorry. That's what this one was. It wasn't a braze plate. It was here, let me just make sure.
So it bolts together in giant sections. So like you could take the bolts out and you could take a section out and take it and pressure wash it. So they goes to these, and then they run glycol on one side of it, and which goes to the building loop, and then they run the tower water on the other side. This is a way better setup for 2 reasons. Because it separates all the units in the building and all the equipment from the actual tower water. So you aren't plugging up strainers all the time or fouling out heat exchangers or having all those issues. You just foul out the heat exchanger up in the mechanical room, and it's a lot easier to maintain because now you're only doing 1 or 2 strainers, and they could constantly do them. So that's a brazed plate heat exchanger. See how the ribs? Plate. So you take the bolts out, and you could take it apart and clean it or pressure wash it or whatever you need. And generally, they have a primary and a secondary. All these supermarket stores, so they have one that's a backup. So you flip to the backup when you need to, and then you can take the other one apart and clean it. And then all the sections are replaceable.
Yeah, so that's what the plates look like.
Yep.
There's the frame and the plate, and then there's just the plate. So, like Kevin said, you can take them out and change them all out. A lot of times we talked about, they do have a bypass, so they do make them back blowable, so you can take the water and then back blow it out, because a lot of times that will help clean out, especially if it's on an open loop. Open loops are awful. It's bird feathers and bird poop. It's just wood.
Everything that gets sucked in an air cooled condenser gets sucked into this tower
and then stuck in the plate and frame.
Yeah, and then if your water treatment guy isn't good, the thing's shit. And let's be honest, a lot of grocery stores let the water treatment go because it gets put on the back burner of maintenance. And they, especially up here, like we have really hard water. So if you run without water treatment for a little bit, say the water treatment company gets fired or maintenance contracts get shifted, or the store manager doesn't know what this bill is and he cancels it and makes the towers just destroyed.
Yeah. The problem is with that, you'll have solenoids on there that blow the water down. And a lot of times those solenoids do foul up. And then when you start having sediment in the bottom of the tower, when people do PMs, they check the chemical, but they never check like how much crap or sludge in the bottom there. That chemical attaches onto calcium chloride. And so if you have a whole bunch of sludge in the bottom, the chemical just goes to that instead of actually going up to the tubes where it should be. So your chemical usage is out the window as well. So then when you do blow down that chemical, blow down your drain, you're blowing out a whole bunch more chemical. Making sure that if you do have any kind of open loop where you do have water treatment, make sure that you are clearing that out and you have no sludge. I made a standard practice that if it ever showed up, even on a service call, open up the blowdown line on those valves. 1, it keeps the valve that you actually moving it every once in a while. And 2, a lot of times you'll clear out any sediment that's just freaking laying in the bottom there.
Yeah, it's when I was an apprentice, we took care of a Unilever plant, and the towers were like massive, hundreds of horsepower, and we'd be in there for days. Me and another apprentice shoveling all the sediment out of a shutdown tower.
Yeah, 100%.
And I mean, dude, just like wheelbarrows full of sediment. It's
That must suck being in like an actual high building. Like if the tower is actually in a high building there in Chicago, you have to get rid of all that stuff.
oh yeah, do we carry down the stairs? We'd have to carry down the stairs till we get to the freight elevator in buckets.
Fun.
No, it was absolutely terrible. I hated that place. It was the worst. It was the worst plant I've ever worked in my entire life. You had to be in full PPE all the time, full sleeves. In the summertime or in the wintertime, it was 110 degrees on the production floor.
What'd they make there?
Soap and then Dove chocolate bars.
What?
Yeah. So one part of the building was soap and the other part of the building was Mars Dove chocolate bars. Complete. Yeah. Oh, animal fat smells so bad when they rented this shit down.
Yeah. When I was doing industrial, I used to work at a place called Mopac. My wife's, what do they do at Mopac? I was like, they pack the mows. You had these conveyor belts with cow hides and it smells god awful. That and any kind of turkey or chicken plant is some of the worst smelling things in the world.
Oh yeah.
Awful.
Guys, we'll do some more basic refrigeration here coming up.
Oil failures. We'll do some oil
Yeah.
failures. Let me give you some time and I'll make some more racks up and I have low pressure system, the helical separators, impingement screen. We'll do some shit.
Then we'll get back to some advanced CO2. Thanks, guys.
Take it easy, guys.